So dear students, in this video, this may be the last discussion of the chapter 2. So the last discussion of the chapter 2 will be energy stored in a capacitor. Energy stored in a capacitor. So the capacitor will be parallel plate capacitor. So in this discussion, we will utilize our old notion of work done or work energy theorem, which tells us work done in a conservative force field will be equals to the energy stored in the process. So as earlier we know, what we did was when a unit charge, unit positive charge was brought from one unit positive charge was when the one unit positive charge was brought from infinity to any point P. So the work done in that process was potential at that point P. So when a one unit positive charge was brought from infinity to any point P, then work done in that process was potential at that point P. Similarly, when a unit positive charge was brought from point R to point P, one unit positive charge was brought from point R to point P. So work done in that process was Vp minus Vr, the potential difference between the 2 points. Okay, so this is work done per unit charge. This is also work done per unit charge, because we are doing work in bringing a unit positive charge. Work done per unit charge. So similarly, in a parallel plate capacitor also, what we will do is we will take unit positive charge from this plate to this plate. Each time we will bring positive charge from this plate to this plate, and we'll make the configuration. We'll bring positive charge from this plate to this plate, and we will make a configuration like this, since positive charge are being brought from this plate to this plate, so all the positive charge will accumulate here, and since all the positive charge are brought from this plate to this plate, so this plate will get negatively charged. So what we will do is we will take positive charge from here to here, and we will calculate the work done in bringing positive charge from here to here, and we will add all the small work done to make the final configuration as this one, which is a parallel plate capacitor. So total work done in making this configuration will be our energy stored by this capacitor. So total work done in making this configuration, this means the above configuration, this configuration by taking small charges. Total work done in making this configuration by taking small charges from one plate to another plate will be stored as the energy of the capacitor. So let's do this thing. So firstly brought a small charge, some positive charge, 1 unit positive charge from this point to this point, this plate to this plate, and let us take, in doing so, our work done is suppose del W1, del W1. Again, bring 1 unit positive charge from this point to this point. So your work done will keep on changing. So for an intermediate point, for an intermediate situation, since positive charges are brought from this point to this point, so these are partially positive now. So for an intermediate situation, let again 1 unit positive charge is brought from this plate to this plate, and in doing so, our work done will be del W dash. And in that very time, let del V dash be the potential difference between the two plates. And let us take, you are bringing uh, you're bringing, suppose some, okay, it is okay, 1 unit positive charge. Okay, suppose in that intermediate time you are bringing some del Q dash charge from this plate to this plate. So in that intermediate situation, let us take, you are bringing del Q dash charge from this plate to this plate. In doing so, you are doing del W dash work in a potential difference of del V dash. So for that intermediate situation, my work done will be del W dash is equals to del V dash into some amount of charge, that is del Q dash. Okay, let us take V dash. Potential differences, let us take V dash. So your work done in bringing del Q dash from this plate to this plate will be del W dash is equals to V dash into del Q dash. So this is the small work done in bringing del Q dash from this plate to this plate. Now total work done will be work is equals to del W dash. Now you are making a configuration from 0 to Q. This will give me work done is equals to 0 to Q. Del W dash is V dash del Q dash. V dash can be written as Q is equals to C is equals to Q dash by V dash. So V dash is Q dash by C. So it is Q dash by C del Q dash from 0 to Q. So work done will be 1 by C Q dash del Q dash. So Q dash del Q dash will be integration of Q dash del Q dash will be Q dash square by 2 from 0 to Q. So W will be 1 by 2C Q square. So work done will be Q square by 2C. So this is the work done in bringing all the charges or making the configuration of parallel plate capacitor. So this can also be written as C is equals to Q by V. So since Q is equals to CV, so work done will be half C square V square by C. So C cancels, 1C to cancel, so it is half CV square. So it can also be written as this way, or it can also be written as in terms of V and Q. So C is equals to Q by V. So work done is equals to half Q by V into V square. V and 1V cancel. So work done is equals to half QV. So it can also be written as this way. So it can be written as Q square by 2C, half QV and half CV square. So this is the work done in making this configuration. Uh, the work done in making this configuration, and this is also the energy stored in the capacitor. So this work done is also the energy stored in the capacitor, stored as in the capacitor. So it will be equals to half uh, Q square by C is equals to half QV is equals to half CV square. So this much for today. Thank you. And this is the end of your last chapter, like second chapter.